Now, chapter 13, exercise. So here some constants are given to you, which you have to use in different problems. Now, example 13.1. A. Two stable isotopes of lithium, Li36 and Li37, have respective abundances of 7.5% and 92.5%. These isotopes have masses 6.01512 U and 7.01600 U respectively. Then find the atomic mass of lithium. Question B. Boron has two stable isotopes, B510 and B511. Their respective masses are 10.01294 U and 11.00931 U. And the atomic mass of boron is 10.811 U. Find the abundances of 5B10 and 5B11. એટલે ફર્સ્ટ ક્વેશ્ચનમાં આપણને એબન્ડન્સીસ આપ્યા છે અને આપણે લિથિયમનું માસ ફાઇન્ડ આઉટ કરવાનું છે. સેકન્ડની અંદર આઇસોટોપ્સના માસીસ આપ્યા છે, બરોબર, અને એમના એબન્ડન્સીસ ફાઇન્ડ આઉટ કરવાના છે. Now see, mass of lithium that is given to you here for 3Li6, it is 6.01512 U. Okay, and its abundance that is 7.5%. Mass of Li37 that is 7.01600 U. Its abundance that is 92.5%. So now atomic mass of lithium that is 7.5 into 6.01512 plus 92.5 into 7.01600 upon 100. Actually, that is 7.5 plus 92.5, that is 100. Solve it, you will get atomic mass of lithium. Now for boron, mass of 5B10 that is 10.01294 U, that is given to you. Suppose for this isotope the abundance that is X percentage, and for the isotope 5B11 mass is 11.00931 U, then its abundance that will be 100 minus X percentage, obviously. Now mass of boron that is given to you 10.811 U. So 10.811 U, that is equal to X percentage abundance of 5B10. So X into 10.01294 plus 100 minus X percentage, that is of 5B11. So 100 minus X into 11.00931 upon 100. Solve this one, you will get X. Once we get X, then after 100 minus X, so we will get the percentage abundances of both the isotopes in boron. Clear to all of you? 13.2. The three stable isotope of neon 10Ne20, 10Ne21, 10Ne22 have respective abundances of 90.51%, 0.27% and 9.22%. The atomic masses of the three isotopes are 19.99 U, 20.99 U and 21.99 U respectively. Obtain the average atomic mass of neon. Now mass of these three isotopes and their abundances are given to you. So you can write now average atomic mass of neon, that is 90.51%, that is 10Ne20. So 90.51 into mass of 10Ne20, 19.99. Then after 0.27%, that is 10Ne21. So 0.27 into mass of 10 Ne21, that is 20.99. Then 9.22%, that is 10 Ne21, sorry 22. So 9.22 into mass of 10 Ne22, 21.99 divided by 100. Solve this one, you will get average atomic mass of neon. Clear to all of you? 13.3. Obtain the binding energy in MeV of a nitrogen nucleus 7N14, given that mass of nitrogen, that is 14.00307 U. So mass of nitrogen atom, that is given to you 14.00307 U. Now we want to calculate binding energy. So binding energy, that is delta M into C square. So delta M, that is the mass defect. So first of all, we have to calculate mass defect. Now mass of proton in free state, that is 1.007825 U, and here 7 protons are there, so multiply this one by 7. So mass of 7 protons in free state, that will be 7 into this one. Similarly, in nitrogen, 7 neutrons are there. So 7 into mass of neutron in free state, that is 1.008665. You will get this much U. Now delta M, that is ZMP plus NMN minus MX. As per that equation, 7 into 1.007825 plus 7 into 1.008665 minus mass of nitrogen atom 14.00307. Solve this one, you will get mass defect in terms of U. Now binding energy, that is delta M into C square. But when your mass is in terms of U, we already proved this thing, 1 U, that is 931.5 MeV energy. So directly multiply this mass by 931.5, you will get the binding energy in MeV. Clear to all of you? Next one. 13.4. Obtain the binding energy of the nuclei 26Fe5683Bi209 in units of MeV for the following data. Mass of Fe atom, that is given to you 55.934939 U. Mass of Bi atom, that is 208.980388 U. Again simple, exactly like previous one. So mass of 26Fe56 atom, that is given to you. Now in this Fe atom there are 26 protons. Total number of nucleons 56. So 56 minus 26, that is 30. That is the number of neutrons. Mass of proton, mass of neutron, that is given to you. So mass defect, that is ZMP plus NMN minus MFE. Here substitute all the values of ZMP, NMN and mass of Fe. Solve it, you will get mass defect in terms of U. Then after multiply it by 931.5, you will get the binding energy of Fe in MeV. Suppose in this one they ask you calculate the binding energy per nucleon, then divide this answer by total number of nucleons 56, then you will get binding energy per nucleon. Then after mass of Bi 83209, that is given to you. In this one, number of protons, that is 83, and number of neutrons, that is 209 minus 83, that is 126. mass of proton and mass of neutron that is given to you. Again, use the equation of mass defect delta M, that is ZMP plus NMN minus mass of Bi atom. Substitute all the values here, then solve it. You will get mass defect in terms of U. Then multiply that mass defect with 931.5. You will get the binding energy in MeV. Clear? 13.5. A given coin has a mass of 3 gram. Calculate the nuclear energy that would be required to separate all the neutrons and protons from each other. For simplicity, assume that the coin is entirely made of 29 Cu63 atomic mass, that is 62.92960 U. Now atomic mass of Cu, that is 62.92960, that is given to you. Now in copper, number of protons, that is 29. 63 minus 29, that is 34, that is the number of neutrons. Mass of proton, mass of neutron, that is always given to you. Now here, the coin that is with mass equal to 3 grams. So first of all, we have to calculate the mass defect for one atom. Then we have to calculate the total number of atoms in 3 gram. And then after we have to calculate total mass defect. So first of all, mass defect per atom, that is ZMP plus NMN minus MCU. Substitute the values and calculate delta M. This is the mass defect per atom. Now here atomic mass number, that is 63. So if we take 63 gram copper, then that is 1 mole substance. So in 63 gram, the number of atoms that will be equal to Avogadro number, that is 6.02 into 10 raised to 23. Therefore, in 3 gram, how many? So total number of atoms in 3 gram, that is 3 into 6.02 into 10 raised to 13 upon 63. So you will get total number of atoms. Now per atom we have mass defect delta M. Therefore in this much number of atoms, how much mass defect is there? So mass defect of 3 gram Cu, that is delta M into this total number of atoms. Then solve it, you will get the total mass defect. Therefore now binding energy of 3 gram Cu, that is this mass, which is in terms of U, so directly multiply it by 931.5. You will get binding energy in terms of MeV. So whatever is the binding energy of that particular substance, that much energy we have to supply it to separate all the nucleons. Clear to all of you? So energy required, that is this, equal to binding energy. Next, 13.6. Write nuclear reaction equations for 1. Alpha decay of 88 Ra226. So 88 Ra226 alpha decay, that is helium nuclei. So for the daughter nuclei, or we can say for product nuclei, Z will be decreased by 2 and A will be decreased by 4. So we will get the reaction 86 Rn222 plus 2He4. Then second one, alpha decay of 94 Pu224. So 94 Pu242, here सुधार जरा. So when alpha decay takes place, Z will be decreased by 2 and A will be decreased by 4. So the daughter nuclei will be 92U238 and alpha decay means 2He4. Third one, beta minus decay of 15p32 and same type beta minus decay of 83bi210. Now when beta minus itself is the electron, so when beta minus decay takes place at that time, the Z value for daughter nuclei will be increased by 1, but A will remain same one. So 15p32, so daughter nuclei that will be 16s32, A that remains same one, Z is increased by 1, plus beta minus decay, and with beta minus always anti-neutrino that is emitted. So E minus plus anti-neutrino, the reaction is completed. Fourth one, 83Bi210. So we'll get 84PO210, then beta minus emission with it anti-neutrino. Then after fifth one, beta plus decay of 6C11 and beta plus decay of 43Tc97. So 6C11 beta plus. So when beta plus decay takes place at that time, Z value will be decreased by 1, but A will remain constant. So 5B11 plus positron means beta plus, and with it the neutrino is emitted. Then 43Tc97. So here we'll get 42MO97 plus positron means beta plus, with it neutrino. Then last one, positron capture of 54Xe120. So 54Xe120, it capture positron. Okay. So if positron is captured, then Z will be increased by 1. This will remain same one. So here I plus neutrino. Clear to all of you? 13.7. A radioactive isotope has a half-life of capital T years. How long will it take the activity to reduce to A 3.125% and B 1% of its original value? હવે એકચ્યુઅલી આની અંદર છે ને આપણે n/n0 that is equal to e⁻⁻t એનાથી બી કેલ્ક્યુલેટ કરી શકીએ. બીજું એક ઇક્વેશન આ રીતે પ્રિપેર કરાય. જો ટાઈમ and number of undecayed nuclei, જો એનો સેટ આપણે તૈયાર કરીએ. At 0 time, number of undecayed, that is n0. Then after time capital T that is the half time. So now undecayed nuclei that is n0 by 2. So you can rewrite this one half raised to 1 into n0. Then again capital T time lapse means total time that is 2t. So half then this one. So 1 by 4 n0, that you can write 1 by 2 square n0. Again t time lapse, so total time that is 3t. Again half of this one, that is 1 by 8 n0, that is half raised to 3 n0. So in this way, after total time t equal to nt, you can write number of undecayed nuclei that is half raised to n into n0. So now we can write total time that is equal to nt, undecayed nuclei that is half raised to n into n0. Now from this one you can write n equal to t by capital T. So n upon n0 here, that is equal to half, and n is replaced by t upon capital T. Now see this 1%. So n upon n0 is 1%, means 1 by 100. We can write that is equal to half raised to T upon capital T. So now take log on both the side. So log 1 minus log 100, that is T by capital T into log 1 minus log 2. Substitute the values of log, then solve it. You will get small t, that is equal to 2 by 0.3010 into capital T, means after this much time, 1% of original value will be there for the activity. The same thing that you can calculate for 3.125% also. But another method is there to carry out the calculation for 3.125%. So when you take half, at that time, if you get this type of percentage of undecayed nuclei, so at that time you can use this particular method. That is very simple. At time t equal to 0, 100% substance is there. Then after time t, undecayed will be 50%. Again after time t means 2t. Out of this one again half will be decayed, so remaining that is 25% only. After time 3t, again half then this one, so 12.5% will be undecayed. So at 40 times 6.25%. So at 5t time 3.125%. So this one is also very simple method. You can use any one. Next, 13.8. The normal activity of living carbon containing matter is found to be about 15 decays per minute for every gram of carbon. This activity arises from the small proportion of radioactive 6C14 present with the stable carbon isotope 6C12. When the organism is dead, its interaction with the atmosphere, which maintains the above equilibrium activity, ceases and its activity begins to drop. From the known half-life 5730 years of 6C14 and the measured activity, the age of the specimen can be approximately estimated. This is the principle of 6C14 dating, which is known as carbon dating process, used in archaeology. Suppose a specimen from Mohenjo-daro gives an activity of 9 decays per minute per gram of carbon, then estimate the approximate age of the Indus Valley civilization. Very simple. Question is lengthy one, but the solution is very simple. Initial activity that is given to you 15 decays per minute. Then final activity that is 9 decay per minute. Okay, final means present one. So here half-life that is also given to you 5730 year. Now R upon R0, that we can write N upon N0. So that is 9 by 15. Okay, and that is 3 by 5. But we have n equal to n0 e raised to minus lambda t. So we can write n upon n0, that is 3 by 5, that is e raised to minus lambda t. So we can write 5 by 3 equal to e raised to lambda t. Now here take natural log on both the side, and then by multiplying with 2.303, you can write in terms of log at the base of 10. So 2.303, this 5 by 3, that is log 5 minus log 3, that is equal to lambda t. But lambda, that is 0.693 upon capital T. So here capital T, that is in terms of air. So directly your answer of time T when you solve this one will be in terms of air. Clear to all of you? Next one. 13.9. Obtain the amount of 27 CO60 necessary to provide a radioactive source of 8 millicurie strength. The half-life of 27 CO60 is 5.3 years. So activity that is 8 millicurie. So 8 into 10 raised to minus 3. But a Curie, that is 3.7 into 10 raised to 10 decay per second. So total that will be 8 into 10 raised to minus 3 into 3.7 into 10 raised to 10. So you will get 8 into 3.7 into 10 raised to 10 decay per second. Half-life, that is 5.3 years. So that is 5.3 into 3.15 into 10 raised to 7 second. Now we have equation for activity, that is R equal to lambda into N. So lambda, that is 0.693 upon capital T into N. So N, the number of undecayed nuclei, that is TR upon 0.693. T that is given to you, substitute its value. R that is given to you, substitute upon 0.693. Solve it, you will get N, the number of undecayed nuclei. Now, for CO, the atomic mass number is 60. So 60 gram CO, that is 1 mole. It implies that now we can use the unitary method like this. If 6.02 into 10 raised to 23 undecayed nuclei are there, then the mass of the substance, that is 60 gram. Then for this number of undecayed nuclei, what will be the mass? So now solve this one, you will get mass of the substance. Clear? 13.10. The half-life of 38 SR90 is 28 years. What is the disintegration rate of 15 milligram of this isotope? Okay. Now, 38 SR90, that is the substance. Half-life, that is 28 year, 1 year, that is 3.15 into 10 raised to 7 second. So half-life, that is 28 into 3.15 into 10 raised to 7 second. Mass of the substance, that is 15 milligram, that is 15 into 10 raised to minus 3 gram. And we want to calculate activity, disintegration rate, or we say decay rate, or activity. After all are one of the same thing. Now, R, that is equal to lambda into N. Lambda, that is 0.693 upon half-life into N. But what is the number of undecayed nuclei in 15 milligram? That we don't know. So we can calculate it like this. In 90 gram, 6.02 into 10 raised to 23 nuclei will be there. Therefore, in 15 into 10 raised to minus 3 gram, how many? So, number of undecayed nuclei, that is 15 into 10 raised to minus 3 into 6.02 into 10 raised to 23 upon 90. Solve it, you will get 10 raised to 20. So, now substitute this value of 10 raised to 20 here and the given half-life of SR. So R equal to 0.693 upon 28 into 3.15 into 10 raised to 7, the whole multiplied by 10 raised to 20. Solve it, you will get activity of this isotope. Clear to all of you? 13.11. Obtain approximately the ratio of the nuclear radii of the gold isotope 79 Au179 and the silver isotope 47 Ag107. Okay. Now Au and Ag are given to you. We know the nuclear radii that is given by the equation are equal to R0 a raised to 1/3. So the ratio of the radii of Au to Ag, that is equal to A of Au upon A of Ag. A of Au, that is 197, upon A of Ag, that is 107. This whole raised to 1/3. Solve it, you will get the answer. Clear to all of you? Next, 13.12. Find the Q value and kinetic energy of the emitted alpha particle in the alpha decay of 88 Ra226 and B86 Rn220. Mass of 88 Ra226, mass of 86 Rn222, mass of 86 Rn220, mass of 84 216 Po, all are given to you. Okay. Now, first we think about the alpha decay for 88 Ra226. So 88 Ra226, so Z will be decreased by 1 and A will be decreased by 4. So we will get 86 Rn222 plus alpha particle 2He4. So Q value, that is mass defect into C square. So left hand side mass minus right hand side mass. So mass of Ra minus mass of Rn minus mass of He into C square. So all these masses are given to you. Substitute and then directly multiply it by 931.5. You will get the answer in MEV. Then for 86 Rn220, alpha decay takes place. So we'll get 84 PO 216 plus 2He4. Again, Q value, that is left hand side mass, mass of Rn minus right hand side mass, mass of PO minus mass of He into C square. Substitute the value of all masses and then directly multiply by 931.5. Your answer will be again in MEV. Clear to all of you? So this Q value energy, which one is released, that is gained by this product in the form of kinetic energy. Clear to all of you? Next, 13.13. The radionuclide 611 decays according to 6C11 to 5B11 plus positron plus neutrino. Half-life, that is 20.3 minutes. The maximum energy of the emitted positron is 0.960 MeV. Given the mass values for 6C11, that is 11.01144 U, and for 6B11, that is 11.009305 U. So now calculate Q and compare it with the maximum energy of the positron emitted. So the reaction given to you, that is 6C11 to 5B11 plus positron plus neutrino. Now maximum energy of the emitted positron, that is also given to you, 0.960 MeV. Mass, atomic mass of 6C11 and 5B11 both are given to you. So Q value, that is left hand side mass, that is mass of carbon minus right hand side mass, mass of boron minus mass of positron. So that is of electron itself. So here mass of carbon minus 6 mass of electron minus mass of B minus 5 mass of E minus Me. So mass of C minus mass of B minus 2me resultantly we will get into C square. So now substitute all the masses here, then directly multiply it by 931.5. You will get the answer in MEV. And then after, take the ratio of this Q value and this maximum energy with which the positron is emitted, then the comparison will be there. Clear to all of you? 13.14. The nucleus 10Ne23 decays by beta minus emission. Write down the beta decay equation and determine the maximum kinetic energy of the electrons emitted. Given that atomic mass of 10Ne23 and 11Na23, both the masses are given to you. So these masses are given. Then the reaction that will be 10Ne23, 11Na23, electron is decayed, -1 E0 plus antineutrino. So here we can write now left hand side mass. So mass Ne minus mass of 10 electron. For right hand side, minus mass of Na minus 11 mass of electron, and this one minus mass of electron into C square. So minus 10 Me minus Me, total 11 Me, and this minus minus plus 11 Me. So resultantly we will get mass Ne minus mass Na into C square. Substitute the values of masses and directly multiply it by 931.5. You will get Q value of the equation. 13.15. The Q value of the nuclear reaction A plus B to C plus D is defined by Q equal to Ma plus Mb minus Mc minus Md into C square, where the masses refer to the respective nuclei. Determine from the given data the Q value of the following reactions and state whether the reactions are exothermic or endothermic. So two reactions are given to you. 1H1 plus 1H3 gives you 1H2 plus 1H2, and another reaction 6C12 plus 6C12 give you 10Ne20 plus 2He4. Then atomic masses of 1H2, 1H3, 6C12, 10Ne20 are given to you. Now see, all the masses given to you are listed first. Then the first reaction 1H1 plus 1H3 give you 1H2 plus 1H2. Okay. Then Q value, that is left hand side mass minus right hand side mass into C square. Substitute the values of all the masses, then multiply it by 931.5. When you solve this one, your Q value that will be minus 4.03 MeV. So when Q value is less than 0, the reaction that is called endothermic. Then another reaction 6C12 plus 6C12 give you 10Ne20 plus 2He4. So Q value, that is left hand side mass twice the mass of 6C12 minus right hand side, that is mass of Ne minus mass of He. Substitute value of all the masses and directly multiply it by 931.5. When you solve this one, your answer will be plus 4.61 MeV. So we can say the reaction is exothermic because Q is greater than 0. Clear? Simple thing. Next, 13.16. Suppose we think of fission of a 26 Fe56 nucleus into two equal fragments, 13 Al28. Is the fission energetically possible? Argue by working out Q of the process, given that mass of Fe and mass of Al. Okay. So mass of Fe, atomic mass of Al are given to you. Then after the reaction, 26 Fe56, okay, fission takes place in two equal fragments. So 13 Al28 plus 13 Al28. So Q value, mass of left hand side, that is mass of Fe, minus mass of right hand side, that is twice mass of Al into C square. Substitute the values of atomic masses of Fe and Al, then directly multiply it by 931.5. You will get answer minus 26.08 MeV. So here Q value, that is negative. It implies that fission is not possible. If Q value, that is positive, then and then only the fission is possible. Clear to all of you? Next, 13.17. The fission properties of 94Pu239 are very similar to those of 92U235. The average energy released per fission is 180 MeV. How much energy in MeV is released if all the atoms in 1 kilogram of pure 94Pu239 undergo fission? Now see the process. 94Pu239. From that we get 92U235. So alpha decay 2He4 plus 180 MeV energy. Now see here, first of all, we have to calculate the number of nuclei in 1 kilogram Pu. So here atomic mass number is 239. So if we take 239 gram, then the number of nuclei will be 6.02 into 10 raised to 23. Therefore, in 1000 gram, means in 1 kilogram, how many nuclei are there? So when you solve it, you will get number of nuclei, that is 6.02 upon 239 into 10 raised to 26. When one fission takes place, then we get 180 MeV energy. So per fission 180 MeV energy is obtained. Then per n fissions, how much energy will be released? So energy released, that is 6.02 upon 239 into 10 raised to 26 multiplied by 180. This much MeV energy will be released. Next, 13.18. A 1000 megawatt fission reactor consumes half of its fuel in 5 years. How much 92U235 did it contain initially? Assume that the reactor operates 80% of the time, that all the energy generated arises from the fission of 92U235, and that this nuclide is consumed only by the fission process. 1000 megawatt fission reactor consume half of its fuel in 5 years. So fuel used half in 5 years, that is given to you. So initially, if we take, means before 5 years, the number of undecayed nuclei N0, then after 5 years we can write N equal to N0 by 2. Now, number of atoms in 1 gram of U235, that is 6.02 into 10 raised to 23 upon 235. This much number of atoms is there in 1 gram. So let's calculate this N0. Then using unitary method, we will calculate the mass. Now total energy of the reactor, that is 1000 megawatt, means 10 raised to 9 watt, that is 10 raised to 9 joule per second. Okay. Now energy per fission, that is 200 MeV. This one is taken from the theory which we discussed. So 200 into 10 raised to 6 into 1.6 into 10 raised to minus 19. So energy per fission released, that is 3.2 into 10 raised to minus 11 joule. Now we have energy per fission as well as energy per second for the reactor. So if we take the ratio energy per second to energy per fission, then we will get the number of fissions per second. So 10 raised to 9 upon 3.2 into 10 raised to minus 11, we will get 1 upon 3.2 into 10 raised to 20. Means number of fission per second takes place this much. Clear? But see here, it is given to you. Reactor operates 80% of time. એટલે આપણને જે 5 વર્ષનો વર્કિંગ ટાઈમ આપ્યો છે એકચ્યુઅલી એના 80% જ રિએક્ટર ઓન હતું, 20% ઓફ હતું. મતલબ કે ટાઈમ ઓફ વર્કિંગ ફોર રિએક્ટર that is 80% of 5 year. So 5 year, that is 5 into 3.15 into 10 raised to 7 second, and 80% of it means multiply it by 0.8. This much second reactor is in working condition. તો હવે નંબર ઓફ ફિશન્સ પર સેકન્ડ જો આટલા થતા હોય તો આટલી સેકન્ડમાં કેટલા ફિશન થયા હોય? તો નંબર ઓફ ફિશન ઇન ધીસ પર્ટિક્યુલર ટાઈમ, એટલે કે 5 વર્ષમાં જે વર્કિંગ કન્ડિશનમાં હતું એમાં. તો 5 into 3.15 into 10 raised to 7 into 0.8 into 1 upon 3.2 into 10 raised to 20. તો 5 વર્ષમાં જે વર્કિંગ કન્ડિશન્સમાં હતું એમાં નંબર ઓફ ફિશન્સ જે થયા that is 4 into 10 raised to 27. પણ 5 વર્ષમાં વર્કિંગ કન્ડિશનમાં જે નંબર ઓફ ફિશન્સ થયા that we can say n0 by 2. So this is n0 by 2. So n0, that is 8 into 10 raised to 27. So this is nothing but number of atoms in fuel initially. Now, if 6.02 into 10 raised to 23 atoms are there, then mass of the fuel will be 235 gram. So if 8 into 10 raised to 27 atoms are there, then the mass of the fuel will be what? So initial mass of U235, that is the fuel, will be 8 into 10 raised to 27 into 235 divided by 6.02 into 10 raised to 23, this much gram, then convert it in kilogram. Clear to all of you? Next, 13.19. How long can an electric lamp of 100 watt be kept glowing by fusion of 2 kilogram of deuterium? Take the fusion reaction as 1H2 plus 1H2, that gives you 2He3 plus neutron plus 3.27 MeV. So per reaction you are getting 3.27 MeV energy, and in this reaction 2 deuteron fuse. Now here atomic mass number is 2. So if we take 2 gram deuteron, then number of atoms will be 6.02 into 10 raised to 23. So in 2 kilogram means 2000 gram deuterium, how many atoms will be there? So number of atoms in 2 kilogram, that is 2000 into 6.02 into 10 raised to 23 by 2, you will get 6.02 into 10 raised to 26. Now this is number of atoms in 2 kilogram. Now when 2 atoms are fused, we get energy 3.27 MeV. So 2 deuteron fused, energy released, that is 3.27 MeV. So when 6.02 into 10 raised to 26 atoms fuse, energy obtained, that is 6.02 into 10 raised to 26 into 3.27 by 2. Solve it, you will get this much MeV energy. So 3.01 into 3.27 into 10 raised to 26 MeV. So 10 raised to 6 EV into 1.6 into 10 raised to minus 19. This much joule. When you solve it, you will get 15.74 into 10 raised to 13 joule. Now power of the bulb, that is 100 watt, means 100 joule per second. It implies that when bulb is switched on, 100 joule energy is consumed per second. So 100 joule energy is consumed in 1 second. Therefore, this obtained energy 15.74 into 10 raised to 13 joule will be consumed in how much time? So time, that is 15.74 into 10 raised to 13 by 100. That is 15.74 into 10 raised to 11. Solve it. Then divide it by 3.15 into 10 raised to 7. So you will get answer in terms of year. And see here, this bulb can be kept glowing for 49,968 years with the help of 2 kilogram deuterium. Clear to all of you? Next, 13.20. Calculate the height of the potential barrier for a head-on collision of two deuterons. Hint, the height of the potential barrier is given by the Coulomb's repulsion between the two deuterons when they just touch each other. Assume that they can be taken as a hard sphere of radius 2 Fermi. So when head-on collision takes place, it implies that the distance between these two deuterons, that is equal to its diameter. So for head-on collision, the distance between them, that is 2r. So that is 2 into 2 Fermi. So that is 2 into 2 into 10 raised to minus 15 meter. Clear? Okay. Now, potential barrier, that is K Q1 Q2 upon R. So K E square upon R. That is equal to K 9 into 10 raised to 9 into E square, that is 1.6 into 10 raised to minus 19 whole square upon R, that is 4 into 10 raised to minus 15. Solve this one. You will get this much volt. Divide it by 1.6 into 10 raised to minus 19. So potential barrier, that will be this much electron volt. Clear to all of you? Next, 13.21. From the relation R equal to R0 a raised to 1/3, where R0 is a constant and a is the mass number of nucleus, show that the nuclear matter density is nearly constant, or we can say independent of A. Now, density, that is mass upon volume. So for nucleus, mass, that is represented as A, radius, that is R, equal to R0 a raised to 1/3. So density, that is mass, that is atomic mass A, upon volume, that is 4 by 3 pi r cube. So that is equal to A upon 4 by 3 pi r, that is R0 into A raised to 1/3, but here R cube. So take a cube of this one. So A raised to 1/3 raised to cube. So that is A. So resultantly, we will get A upon 4 by 3 pi R0 cube into A cancelled. So here we can see this is the constant one. So it is proved. Clear to all of you?